Good afternoon, everyone, to the fifth problem solving session of the course Fundamental of Semiconductor Devices, NOC 24E02. Today is February 24, week 5 for these sessions. My name is Amit. I'm a PhD student at ISC Bangalore. Quick summary of the previous session. We talked about we classified the materials in terms of their electrical conductivity denoted by this symbol sigma. In metals, insulate, and semiconductor, we saw the semiconductors are a class of materials which have their tunable conductivity, so to speak, by the virtue of doping. We also saw the origin of a band gap in a semiconductor, that is when an electron is there. So we saw that there are these two bands that originate, conduction band and valence band, and there is some specific forbidden energy gap. Electrons can reside here or here, but not in this forbidden gap. And the reason for this was that when when a large number of atoms, for let's say, were brought together, their orbitals overlapped, and which gave rise to these two bands, and in between this region in which no electrons can reside. We also modeled that using how does the electric potential look. We saw that it may look something like this, given by the Ronick-Penny model over here. And so this is your potential versus x, let's say, the position. This is the Ronick-Penny model, and then we saw that something called the band structure. So when this diagram that I have over here is called band diagram, because this is E versus x, this dimension is x. However, if you draw the EK diagram, E versus K, this is also known as band structure. We saw that they look something like this. Let's say this is again your valence band, this is your conduction band, and this is your band gap. K is a wave vector, 2 pi by lambda. This curvature was something which gave us the a very unique entity called the effective mass, M effective or M star. For electrons, we saw in the conduction band, or holes respectively in the valence band. And these are just the states that are there. However, an electron has to occupy them. Okay, so this is where electrons can reside, but it's a probability of occupation. We saw that through the Fermi Dirac statistics, which are followed by fermions. That is essentially your half spin material, half spin particles. And we saw that the electrons will be residing based on this probability, that Fe 1 plus exponential E minus EF over KT. So at E equal to EF, that is energy of occupation at energy E. When E equal to EF, this theoretical construct, the probability of occupation is half. That is supposed to be the Fermi level. It's noted by EF term over here. However, if the energies are greater than EF, higher than Fermi level, above Fermi level, so this term comes out to be greater than 1, and the probability will be less than half. And for at absolute zero temperature, we saw that it looked exactly like the step function. This is just the probability. However, where are the states which denoted this using the density of states in a 3D system, which was directly proportional to, we saw that directly proportional to square root of E. Electrons in conduction band, again holes in valence band, and the total concentration of carriers, let's say electrons, can be arrived at integrating this dE Fe dE, right, from EC to infinity. And we saw that we made some assumptions, and we got a good expression like n equal to nc e to the power ef minus ef over kt, right? And this is what I'm talking about here, that n was nc exponent of ef minus e over kt, something like that. And again, this is for intrinsic means there's no doping. However, when you dope it, things change. So for instance, by doping, you can introduce some levels inside this. Okay, so let's say if I dope it, denoted by this blue line here, you can get this something called the donor level ED. This means now the electrons, even at room temperature, it is possible that some electrons gain some energy, the thermal energy that is, and just jump to the conduction band, and thus they can contribute to the electrons. Similarly, we saw something called the acceptor level, which you usually in the lower half, a good acceptor. In that, what can happen, the electrons are there in valence band, they can jump to this acceptor, this energy level, and thus now the electrons, now the holes can contribute, because now holes can move relatively freely. Okay, finally, just a second, for third week, we use these understandings to learn something about the traditional forms of Ohm's law, that is V equal to IR and J equal to sigma E. J is the current density, E is the electric field, and we saw that this was given inherently by something called the drift, Vd equal to mu E. We saw it with this diagram, this drift velocity versus the electric field E, and it looked something like this. The left half where you see the linear performance was the low field regime, this was the high field regime, and yeah, in the low field regime Vd is equal to mu E, where mu is the mobility. So for there is the mobility of electrons corresponding to the drifting of electrons, and similarly for holes. We also saw another construct called the diffusion, which arose due to the concentration gradient. So for instance, there are a larger number of electrons on one side, lesser on the other, the corresponding, and they'll diffuse from one side to the other. And we saw that in a non-uniform doped semiconductor there can be a slope in conduction band, right? And we did a small derivation to arrive at that d by mu equal to kt by q. This was the Einstein relation. And we also saw that carrier density does not only depend on the let's say doping, drift and diffusion. If you shine light, there can be generation, and there can be recombination also. So we'll see a slight hint of these two processes, generation and recombination, today. Finally, we put this understanding to see how a device is actually working. Till now we are only talking about semiconductor physics, that is the concentration gradient and the density of states, the drift, the diffusion, generation, recombination. We took a device and applied these concepts of semiconductor physics to see how will that device function, and we took a very simple device called the p-n junction. That is on two semiconductor pieces. One is p-type doped, one is n-type doped, that is acceptor type and donor type, and we bring them together. We saw there is a depletion region will be formed in the equilibrium region. This is what we saw, the abrupt p-n junction. We also saw a few examples, the p plus n or n plus p. This p plus denotes that p side is highly doped, n side is moderately doped. We saw how do the charge profiles look like. We saw the depletion approximation, the peak electric field. This is the depletion with W, right? And the built-in potential, because if we saw their band diagram, it looks something like this in equilibrium, that is, right? This was EC, this was EV. In equilibrium, EF will be flat, and we saw that the banding that happened was the VBI, the built-in potential for this p-n junction. When you can apply some bias to that, hook it to some electrical battery. If the polarity is like positive terminal is connected to P, this barrier will shrink a little bit, and thus a large number of electrons or holes from the other side can flow. This is a bipolar device, by the way. Because that happens primarily because now the minority carriers, for instance, which are holes in this case, they can diffuse from this side to this side due to the fact that this barrier has been lowered. And yeah, we also saw an example of high level injection. High level injection essentially means that you're pushing in a lot of current. That means the carriers, the holes or electrons that you're pushing are much larger than the background impurities that are there. We also saw the p-n junction under reverse bias, and the key thing was the reverse saturation current. Just to reiterate, the expression looked something like this: QV applied over KT minus 1. This was the reverse saturation current. That is, even if you are not applying, you are applying a negative bias, there will still be some current flowing, which is the reverse saturation current. And associated with the junction capacitance, I'll start in fact with because reverse bias I was not able to denote much time, so I'll just start with the discussion about the reverse bias itself. So on the screens now you have the typical the three ways in which you can bias a p-n junction. So on the extreme left is the equilibrium. You can see the EF is flat, and this is the built-in potential that I was talking about. Just to reiterate, what would have happened, this is the metallurgical junction. This is the metallurgical junction, and when this was formed, what would have happened is that there are excess of electrons on the right side. So the electrons would have, due to diffusion, they would have moved towards the p side where they were much lower in concentration. While doing that, they left behind the positively charged donor ions. Similar thing happened. So natural electric field was set up, which exactly counterbalanced the diffusion of the carriers. So it's a dynamic system in that way, and thus which gave rise to this built-in potential, because you see there's an electric field that is associated with this this positive charge and negative charge separated in space. There will be electric field that will exist, and correspondingly to electric field there will be a electric potential, which I have written over here as VBI. That is we call this the built-in potential. Now what we did was that we discussed the you look at the rightmost curve, which is for the forward bias. So this is for the forward bias. In this, as I told, we connect the positive terminal of the battery. The magnitude of the potential that are being applying is VA to the P side of the PN junction, and you can see that the junction width, depletion width, has shrunk a little bit. And what essentially happening is that now a lot of electrons can now travel from right to left, which was earlier, which was not possible because its electric field was existing. Now this barrier, so to speak, has been lowered. Speaking in terms of electrical energy, this barrier has been lowered, and thus the electrons can flow over there, and holes similarly can flow to the other side. And you can see the Fermi levels have now split. There is no one Fermi level, which makes sense because this system is no more at equilibrium. So we denote that something called the quasi-Fermi levels, EFN and EFP. What happens when you apply reverse bias? By reverse bias we mean that the P side of the PN junction is connected to the negative terminal of the battery. So you see the VR over here. So VR will be a positive quantity, plus 10 volts, plus 5 volts, whatever, and the positive terminal of the battery is connected to the N side. One clear thing you can notice, the depletion region has widened as compared to the system in equilibrium. And another thing you can see that the effective potential that is dropping across the junction has now increased, is VBI, what the original was, plus VR, whatever potential you are applying. Similar thing happened here. So you are applying, originally there was VBI at equilibrium, you see this term over here, minus VA, we decreased because this was potential which we had externally applied. Here it simply gets added up. Alright, and you can see that the depletion, as I told, the depletion width has increased, and there's more severe band bending in this case. And this is the reverse bias that I was talking about. Now a very small amount of current will flow, and we saw that its density was Js, right, which depended on the I do not recall the expression, but as far as I remember, it was dependent on the diffusion constants, the diffusion lengths, and the minority carrier concentrations from N side as well as P side. So these were the two terms that we had. This was where we left off in our last session that we had. A couple of problems that I could not cover regarding the reverse bias of the PN junction. We'll discuss them here. So the first question for today is that we need to determine as to what region of the IV characteristic of a PN junction does tunneling affect. So we need to analyze the IV characteristic of a PN junction, and with this phenomena called tunneling. So I had introduced tunneling a bit in our first session, if you remember, where I was talking about the band gap formation and other principles related to that. So tunneling is essentially quantum mechanical phenomena. I'll talk a bit more about this, but let's just, for the sake of completion, let me draw the IV characteristic of a typical PN junction. So this is current versus voltage, and this is how the characteristic typically looks like. This is what we typically refer to as the knee voltage. This is the forward side in the first quadrant, and in the third quadrant we draw the reverse characteristic, which looks something like this. The voltage here at which the current rises sharply is called the V breakdown. This is in the third quadrant, where current and voltage are both in the negative direction. This is otherwise known as forward bias, while this region here is known as reverse bias. So this is what we had seen in the previous session. Now let me talk a bit about what do I mean by tunneling. So I'll remove for the timing, for the lack of space, I'll remove this characteristic. We will come back to it again, but let's just get rid of it. So what do we mean by tunneling? So very simply, to explain this, I'll first draw what I draw is the potential V versus the position X. And let's say some particle is traveling in this direction. It's a free particle, so it has some energy, the total energy corresponding to whatever this level is. And let's say this particle encounters a barrier, let's say from x equal to a to x equal to b. This is the potential barrier that it acquires. So it's the potential is 0 all along the x-axis except in the region between a and b. And let's say this is what we call the energy barrier or the potential barrier. Let's say we call this energy barrier, and let's say some value is v naught, the potential v naught correspondingly. So classical mechanics tells me is that if a particle is coming from the left side, that means when its position is x less than a, and if the total energy of this particle is less than the energy of the barrier, which is v naught, which you can see clearly is the case, that there is no chance that the particle will be found here. That is, in other words, the probability of finding this particle on any position x greater than b is 0. It's the same thing I'm saying, the particle cannot be found here. Essentially, it cannot cross this barrier. Classical, in terms of classical mechanics. Quantum mechanics on the other side, which I'm going to determine, which I'm going to now illustrate in the color blue. So again, same thing is happening. A particle is coming, let's say same particle, with the same energy, just drawn a bit different for the sake of clarity. So again, same particle is encountering this barrier between x equal to and x equal to b. Again, the energy is higher than the total energy of this incoming particle. Now quantum mechanics is that there will be a finite probability of finding the particle on the right side of this barrier, that is for positions x greater than b, because from x greater than b the energy barrier ceases to exist. It does not exist for x greater than b. Its potential is 0. Quantum mechanics tells me that there's a finite probability of finding this particle, this incoming particle, even on the other side of the barrier, even though the total energy of this particle was lesser than the energy barrier. The crux of this lies because classical mechanics is a deterministic world, right? You can say with certainty whether the position of a particle is x equal to 5 centimeters, its velocity is 10 kilometers per hour, and so on and so forth. In quantum mechanics, we do not say that. Quantum mechanics is not a deterministic world, but a probabilistic world. What I mean by that, when we talk in quantum mechanics, in terms of quantum mechanics, we always talk in terms of probability. What do I mean? The probability of finding a particle at, let's say, x equal to 5 centimeters is 0.999. It's not 1, right? We always means we say 0.999 is very high probability, is very close to 1. So there is very good amount of certainty that we'll find the particle at that specific position. Similarly, it goes for momentum, energy, and so on. There are other nuances, other depths to it. For instance, the Heisenberg uncertainty principle explains these trade-offs. For instance, for those people who are inclined towards the more physics side, they can read up on these things. I'll not go into those details, but just an overview that quantum mechanics is a probabilistic one. That's the whole takeaway from the tunneling. And this effect where you can find a particle on the other side of the barrier is known as tunneling. So essentially what has happened, rather than going over the top, it appears as if this particle has simply tunneled. This phenomena is tunneling and is peculiar to the quantum mechanical world, not the macroscopic world, but when the dimensions shrink to micrometers and nanometers even. Okay, so now we have talked a bit about, now we have some idea about what tunneling is. Now let's apply the understanding of this quantum mechanical tunneling to this problem. Okay, so let's first analyze the options a little bit. So what we are talking about. So the question here talks about of two regions. Okay, let me change the color again. So it talks about what happens in forward bias and in reverse bias. Okay, each option considers that, and you can see that reverse bias, we don't even care, it's the same in all the 4 options. So let's first talk a bit about what happens in the forward bias region. Okay, and let me analyze this. This is the typical the p-n junction in equilibrium. You can see that no bias has been applied, and let's say I'm talking about the case where both the regions are heavily doped. the p side and the n side of the p-n junction heavily doped, and they are usually denoted by p plus n plus symbol. Highly doped means moderate doping is, let's say, 10 to the power 16 or 17 per centimeter cube. High doping, you can say, is 10 to the power 19 or 10 to the power 20 per centimeter cube. So we're talking about very highly doped regions. Okay, so let's consider this case. So when both the regions are highly doped, so how will the band diagram look like? So you can see the band diagram for this corresponding structure I have drawn here. Remember, this is at equilibrium. How do I know that? You can see that the EF, the dashed line in this figure, is horizontal. That means the Fermi level is flat. So, and also alternately you can see the EFP. So again, on the left side you have P plus, which is, you can see over here. On the right side you have N plus, which you can see over here, and the EFP is equal to EFN. So that's another indicator that in this PN junction we are at equilibrium. And otherwise you can see the valence band, the conduction band, and so on. So one thing you can notice that this is slight error in the sense that this must be EV and this must be EC, and essentially there's some error in the figure. And please, one more thing I want to point out is the energy is Q times V. So when the electronic charge is there, so Q is usually negative. Sometimes these errors crop up. So let's move on. So this is EC, this is EV, and this is the band diagram that I have drawn at the equilibrium. And you can see the doped, heavily doped regions over there. Another thing that I want to point out is the depletion region W. So if you recall the expressions of the depletion widths, right, they inversely dependent on the doping. So higher the doping, lower is the depletion width. Again, here we have very high doping P plus N plus. So depletion regions here that we encounter are not even 1 microns. In fact, much smaller than that. They enter into the regimes of a few nanometers. Okay, and that is essentially what I'm talking about. Is this distance B minus A. Okay, I'll keep on bringing the width of potential barrier over here, so you can see the similar figure is happening, somewhat similar is happening over here. Okay, so now what do is that let's try to analyze after applying some low bias. So this is, let's say, case A. Okay, I'll say low forward bias. So this is the case of a low forward bias. And how can I say that I've applied a forward bias? You can clearly see that EFP and EFN are no more the same. So this means I'm applying some bias. And another thing you can see is that this has shifted a bit towards the upwards. So that means the total band bending is no more VBI, the built-in potential. It's rather something VBI minus some whatever low forward bias that I'm applying over here, denoted by this V1. Okay, so what you can see is that even after the shifting, and please recall that on the N plus side, that is on the right side of this band diagram, you have the occupied states, these are filled. However, on the other side, below EFP, above EFP, on the P plus side, there will be empty states. So what can happen is that if this region is thin enough, how thin? As I told, a few nanometers, that is a B minus A is very small, order a few nanometers or even smaller. The occupied the electrons which are residing in these states, the occupied states, they see an empty state over there and they can simply tunnel through, which I have been talking about the quantum mechanical principle of tunneling. This is also known as the band to band tunneling, because the electrons are moving from one band, that is the conduction band on the N plus side, to the valence band that on the P plus side. So band to band tunneling. All right, so that's what's happening. And what's happening is now the carrier is being transported, and if the carrier transport, now the electrons can be collected on the other side, right? So essentially they have recombined over here. The whole principle of that, the circuit is complete. The electrons are being injected on one side, they are traveling to the other side, and they can now go to the battery, right? This is in a forward bias, please remember that. Okay, circuit is complete, so current will start to flow, and this current is primarily very prominently tunneling. Now let's increase the bias a bit more. So let's say this is the case B. Let's call this moderate forward bias. The case B. what happens is that again you can still see that there is still some overlap between the empty states on the p plus side and the occupied states on the n plus side. This means some band to band tunneling will still happen, but its magnitude will be reduced. Why is that the case? Because the overlapping between the occupied states here and the empty states here, you can see, is reduced. So if I choose a different color to make my point, now the overlap is only in this region. This is the overlap here. Now compare the overlap on this side. So think of it this way: the more the overlap, the higher is the probability, because there are more number of electrons here. If the probability is the same, so more number of electrons can now tunnel. The probability is the same. The total number of electrons tunneled will be probability times the total number of electrons available. So here the overlap is more, so the total number of available electrons are more for a given probability, the more number of electrons will travel. However, this thing is reduced because fewer number of electrons are available for band to band tunneling. So which we'll see is that the tunneling current will start to reduce. But we can also see now is what starts to happen is standard the injection, the drift of the minority carriers across the depletion width will now start. Here the bias was low, very low. That is, we have not even reached the knee voltage. If you recall the knee voltage, I'll draw that diagram. Yeah, the IV characteristic only in the forward region here. So this is the region A, case A, right, where the current is very low. The drift is not even happening. So the current due to drift is non-existent. Here there is some drift. Okay, so there's some electrons are still drifting across the depletion region. Now what I'll do is now let's increase the forward bias even further. Okay, so let me call this case C, and we call this, let's say, high forward bias. So what's happening is that now you can clearly see there is no overlap. The overlap has completely gone away. Now if the overlap has gone away, now there is, you can see this is like here. So we can see here that there is no overlap. No overlap means no band to band tunneling. So there will be no tunneling current. However, now the prominent mechanism will only be the drift of the electrons that we had studied in the last session of the typical, you inject the electrons from the n side, they come to the near the boundary of depletion region, then they drift, and then as soon as they come to the p region, they diffuse and they recombine, and then thus the circuit is completed, steady state is achieved, and we get the current flowing through the diode in the forward bias condition, right? So that is the high forward bias case. So now let's complete this whole picture into this diagram. So what you can see is that the region here, so this is the A region that I'm talking about, region A. In the low forward bias, the current is due to tunneling. You can see a sharp rise in the current over here. What's going to happen is that if you increase the bias even further, so this is the case, let's say, when V is less than Vp, forward bias is less than Vp, this potential. And this is the case when V applied is greater than Vp but less than some Vv, this thing between these two. So what's happening what's happening in this case B? So in this case B, what's happening is that tunneling current is reduced, but some drift current has come, but this drift current is again not as much that it can compensate for the decrease in the tunneling current. And after this state, after that is higher forward bias, is V greater than Vv. This is VA, V applied. This is the again voltage V applied, x-axis, changing the forward bias voltage. And in this region, in the region C that you see is the high forward bias, and this is only the drift current that is flowing through your PN junction diode. And there's peculiar thing which is happening in this region, that as you are increasing the voltage, the current is reducing, which is the negative resistance region. R is del V over del I, right? In this region, delta V is positive but delta I is negative. This is negative resistance region. And this kind of a device, this is also known as, this is the characteristic, by the way, of a tunnel diode. This is the characteristic of a tunnel diode, and how it's manufactured is that the two regions are very heavily doped, and you can see that how we obtain this kind of a characteristic. Band to band tunneling happens in this, and tunneling reduces but drift is not sufficient. Finally the drift takes over and tunneling ceases to exist. So now we can go back to the problem and we see that, okay, so what will happen if that only one side is heavily doped? Then what's going to happen is that depletion region is only going to extend on one side. We saw in the last session that when we had p plus n junction, right, and we found the depletion width, we found that almost 99 to 100% of the depletion width was in the n region. In that case, if I remember, it was a micron or something, right? So typically for moderately doped p-n junctions, you will find that kind of a width. Tunneling probability depends on the width of the barrier, also on the height of the barrier, but on the width of the barrier in this case. So if this width, that is b minus a, the barrier width b minus a, or in this case depletion region, depletion width w, if it's not few nanometers or lower, the tunneling probability will be very small. Tunneling probability depends also on the overlap, but depends on the other factors. Among them, the prominent is the barrier width, that is b minus a, or the depletion region, which is in our case. So that's why if it's heavily doped on one side, the depletion region will be on the low doped side, right? And thus again the tunneling probability will be very low. Okay, so what we see is that this effect then now you will not observe in the in a p plus n or n plus p. So it has to be heavily doped on both sides, and we see tunneling happening when there is a low forward bias and the junction is heavily doped on both sides. So we see junction has to be heavily doped on both sides and in low forward bias. So this option seems correct. No, if it's on one side, tunneling cannot happen because depletion width will be too large. High forward bias, no, high forward bias, you see it's a drift that will be dominant. So this is incorrect, and high forward bias again will not be correct. So it seems that option A is the only correct. But I'll also try to go through the reverse bias side of this problem. Okay, so we had talked a bit about the reverse bias. So this is the diagram from our previous sessions, and as you can see, when we apply reverse bias, the depletion width widens a little bit because now more mobile carriers are depleted near the boundary, otherwise neutral boundary, and you can see the effective banding will be the built-in potential which was there at the equilibrium plus the reverse bias VR that you are applying. Note the polarity that I'm taking. VR will be a positive quantity in this case, and thus you can see the total banding will be VBI plus VR. Now, one thing to notice is that you can again start to observe that there is an overlap between the bands, right? There can be an overlap between the bands in this case also. Okay, so what I'm going to have again is that, however, that will not have, this overlap will not happen when there is no bias, or when there is low reverse bias, because let's draw the diagrams in that case. I'm going to draw it here itself. So this is EC, this is EV, and let's draw the EFP and EFN. Okay, so what they are not this. I'll be more clear, one second. So you can see EFP and EFN are not the same level. So what I'm doing is this is low reverse bias, and let's say this case is moderate to high reverse bias. So you can see that again there is no overlap because the filled electronic states I'm going to show in the blue color over here, they are here, right? These are filled states, but there is no overlap because the empty states are here in the valence band on the p plus on the p side. There is no overlap, so the question of tunneling does not arise. However, if you say this case, when you apply more and more reverse bias, the bending will be more severe, and such a case can arise. So now what's happening is that the electrons are residing here, right? And you can see on the other side there are empty states. These are filled. So similar to the case which we saw in the previous slide of a forward bias of tunnel diode, the electrons can now tunnel through this barrier, again simply band to band tunneling, right? But there is a catch. Remember, I told you it depends on the width, and we typically we notice that the depletion width increases, right? And if, let's say, if a standard is 1 micron, when we apply reverse bias, this will be even more than 1 micron. Okay, so moderate to high reverse bias can result in tunneling, but again, for that you need highly doped p plus and n plus regions. For moderately doped regions, usually it's not that prominent. That's what I mean to say. Okay, your standard mechanism which we had studied in the last session of the reverse saturation current will still hold. That is still flowing. But what I'm saying is that because for moderate dopings the depletion will be so high, the tunneling probability will be reduced massively. Okay, so that's the thing. Tunneling, again, just to summarize, the tunneling is highly dependent on a few factors. One of them is the width of barrier. Also, we did not talk about much in this case the height of barrier. Remember the v naught that I had drawn in the previous slide, that this is the v versus x. This height was v naught, b minus a was the depletion of the barrier width rather. And also we saw that in case of the band to band tunneling, it also depends on the so called overlap of the filled states with the empty states. There's no overlap here, you can see that, no overlap, because there's nothing to go here to. This is the band, is the forbidden energy cap. Okay, so just keep these things in mind, because sometimes in competitive exams they can directly ask the question where this tunneling arises in case of p-n junction. So tunnel diode is the example that you can see. Try to remember its IV characteristics. And so as far as this question is concerned, we had seen only one option is the correct, and I also explained how it on moderate to high reverse bias there can be tunneling, but there's a big if, in the sense that the p and n junctions again have to be heavily doped, because otherwise the depletion will be large, tunneling probability will be very small. So that's it for this problem, and we'll now move on to the next one. So the next question we have is that which of the following statements are true? And it is to be noted that more than one statement may be correct. So just a side note, in such kind of problems you need to be careful. So for instance, let's say this question has two correct answers. You need to tick or mark both of them. If you mark only one correct, then you'll still not be awarded any marks. And this is important, because let's say this has three options correct for so what happens in that case, even if you give 10 minutes of your time and you mark two of them correct, but you for whatever reason are not able to arrive at the answer for the third correct answer, not able to mark, you wasted your 10 minutes, but you'll still not get the marks. So my advice is that you attempt these questions only when you are certain of arriving at all the correct answers, because these kind of questions may take some time. Okay, so just keep that in the back of your mind, because this is a very common format for gate examination, your competitive exams. So just keep that in mind. So in this question, there may be more than one correct option. The first option relates to the avalanche breakdown. We'll talk about that. Second option relates to the zener breakdown. Then we'll talk about zener breakdown. And finally, third and fourth option relate to the depletion capacitance. So what I'll do is that I'll go over these three topics one by one. So let's just first consider the avalanche breakdown. Okay, so in the avalanche breakdown, what this avalanche breakdown arises in the when we bias p-n junction diode in the reverse side. So this is the unbiased uh, p-n junction. You can see the Fermi level is flat, and there's some built-in potential voltage. When we apply a negative bias Vr to this p-n junction, you can see that the depletion region is widened as compared to the unbiased one. Right, this is the reverse bias. It has widened a bit, and you can also see the electric field has increased in intensity. It's denoted by this longer arrow of the electric field E vector. Also, you can see the EFP and EFN have split, and the total banding, that is from P to the N side, you can see is VBI plus VR, the bias that you are excuse me, the bias that you are applying. Okay, so when does so you must have drawn this diagram quite a few times now. So this is your IV characteristics. First quadrant is your forward characteristics, and then what you have here is something the reverse characteristics. So you see at certain point of time, at certain voltage, VBR or the breakdown voltage, the huge amount of current starts to flow. This is just the reverse saturation current, but at certain reverse voltage, VR equal to VBR, huge amount of current flow. So we need to understand as to what is happening at this point of time, at this reverse bias, what is happening. So let's do that. So for this case, let's just consider an electron which is just sitting on the boundary of the depletion region on the p side. So what's going to happen? So as you increase, let's say increase the reverse bias slightly more, what's going to happen? Depletion region will widen, right? Depletion region will widen. Now this electron which is sitting here now will start experiencing electric field. Electric field is from n side to the p side, and remember the electronic charge is negative, so this is a negative charge, mobile charge carrier, this electron, right? So q times e, the force, it will start feeling a force on the in the positive x direction. So this is your positive x direction, I cap. So this electron just sitting over here, just as we slightly increase the reverse bias on the negative side, obviously we're increasing the reverse bias in this direction. So this electron will start now experiencing an electric field, and there's a force in the positive x direction, right, which I am denoting it over here. So you can see this is the same electron that I have drawn over here. So this is, so just for the sake of completion, let me draw that. This is the p side. Rest of the diagram I'm not drawing. Okay, so rest of the diagram I'm not drawing. This is the depletion region that we have. Essentially what I have done, I have just zoomed in as to what is happening over here. If you see the picture in the depletion region, I have just zoomed it out over here, right? So what is happening, this electron is now here, and now it will start, as I told, it will start experiencing a force, F equal to minus E, the electronic charge, times electric field. This is also in the negative direction, so this force will be in I cap, positive x direction, and this electron, if it's at rest, it will start moving in the positive x direction, which you see over here. It has started moving, and this is the lattice atom. I'll use again the different color, which is blue. Okay, so this is our lattice atom. Now it can happen, because please remember this depletion region is usually very wide, micron or so. So it can happen, this electron that is traveling in this direction, and it will gain some velocity. Why? Just simply apply your classical mechanics that v equal to u plus at. So even if the initial velocity is 0, after a certain point of time, or v square equal to u square plus 2as, let's apply that, v square equal to u square plus 2as, even if u is 0, this acceleration is nothing but force by m effective, m star, and s is the distance traveled. So this is the distance traveled I'm talking about, s, when this electron will encounter a lattice atom. Okay, it can so happen, if this velocity is high enough, if the kinetic energy, that is half mv square, is high enough, what it can do is it can knock out an electron, a bound electron, from this lattice atom. What will happen? Now you have two electrons, one the original one, so the direction is not changing, this is just to illustrate as to what is happening. Now there are two electrons. Now after, let's say this distance is s1, now these two electrons will now travel further, and let's say after traveling a distance s2, they again gain sufficient energy, they can again knock out another electron from here. Now please note that s1 and s2 have to be sufficiently large, because a is constant, but your velocity v has to be sufficiently large in order to have sufficient energy to knock out an electron from these lattice atoms. Okay, and such a process can just you can see a geometric progression or even an exponential rise. So what happens is that just within a few hundreds of nanometers or a few microns, which is the typical depletion width for a reverse bias region, this depletion width w, right, what you can see is that at a certain breakdown voltage, this, why is this important? Because this breakdown voltage plays a role in the depletion width w. Just recall your expressions, because w also has a square root dependence on vbr. right? We'll see also in the couple of slides later that that is the case. So if VBR is large enough, your W will be large enough, and also um, your peak electric field will also depend on that, right? Because if we know the peak electric field, or the Emax, right, it was something right, ND times Xn, directly proportional to this, the magnitude of it, right? And your magnitude of W was proportional to VBI plus VR. So if you increase VR, you increase W. That means this, you can now electrons can travel further more distances, and chances of avalanche increase. Similarly, if W increases, Xn also increases, and this Emax also increases. Emax will increase your F, the force that is feeling, and the force increases, the velocity also increases. So essentially, when you increase VBR, all these effects come into the picture, and what you can have at a certain VBR, all of a sudden, rather than just one electron traversing, if the energy is high enough, a huge amount of electrons will travel, and thus the current will rise very sharply, which we see over here in this region, right? This phenomena is known as avalanche. That is, a single electron with sufficient kinetic energy will knock out an electron from lattice atom, and so on. This effect will be compounded. So you can see this here. Now the question, if you recall, was dependence of temperature, right? So how does it depend on temperature? So let's see that now. I'll analyze temperature in the green color now. So till now I've established that what avalanche is. So let's just see, as temperature increases, what's going to happen, the lattice vibration also increases. So this atom that you see, please remember there are nearby atoms also, so this must have traveled to other nearby atoms, right? I have just drawn a picture only where the electron is being knocked out. So when lattice vibration increases, now what it can happen, this electron has more probability of colliding with a nearby lattice atom. And note that this is, it may not have sufficient, because it needs to travel S1 in order to knock out an electron. If it collides before S1, it will lose its energy, right? So lattice vibration increases. This implies probability of electron losing its energy prematurely. The word prematurely here means it does not still have sufficient energy to knock out an electron, increases. What this means, probability of knocking out electron decreases. This implies probability of avalanche decreases. So as you increase the temperature, lattice vibrations increase, means now this electron can lose its energy early, rather than, so it will not be able to knock out an electron from this green atom, for instance, and thus your avalanche will be delayed, right? So this is known as a positive temperature coefficient. So you increase the temperature, the value of that entity increases. It's called a positive temperature coefficient, which we are seeing in this case. So this is the analysis for our avalanche breakdown, right? Now let's consider second analysis, which we have, is for zener breakdown, right? So in this part, zener, it needs that high p and n doping. Okay, so let's just draw that that diagram first. Okay, so this is the first, I'll draw the without any um, without any bias. So what we have is EFP equal to EFN. So let me draw the Fermi level. So this is heavy doping, so this is how it will look like. We have also seen in the previous discussion on tunnel diode, this is how the band diagrams used to look. And again, please remember that in this case, this is P plus, this is N plus. This depletion with W is very narrow, a few nanometers also. Okay, and so this is your EF, this is our EC, this is our EV, and this is EF. Again here this is your EC. Because it's heavily doped regions, this is how the band diagram will eventually look, right? So now let's apply a reverse bias. Zener breakdown is another mechanism in which a device p-n junction diode breaks down in reverse bias. All right, so this is the W that I was talking about, the depletion width. All right, so when we apply a reverse bias, so we know we typically know what happens is that the bends shift even further downwards, right? So let's I'll try to do the draw the same diagram over here. So the band bending will be a bit more aggressive now. So I'm not changing the left side, so to speak. Okay, so the left side remains the same, and also the band gap naturally throughout the structure will remain the same. So EFP will again lie somewhere here. Now why EFP? So this is your at equilibrium, this is reverse bias, and somewhere will be here will be our EFN. So this band bending that you see over here is nothing but VBI plus the reverse bias voltage that you are applying. Here the band bending is only VBI, the total band bending. So again this is your ECEV and whatnot, so let's not worry about that. Again you see the depletion region naturally will widen a little bit, because we know the expression, it depends on the square root and other factors of the applied voltage, right? So now what you can now here see is that now why does this, so this is essentially again similar to a tunneling phenomena. Okay, so what's happening here is I'll draw, so these are the field states over here, the P plus side, these are the field states, and these are relatively empty states above EF. You know the probability of finding an electron is less than half, so I'll call them the empty states. And also note there's a strong electric field that is being applied here, and this depletion with W, because please remember we are heavily doped, this is P plus N plus junction, so there will be a very narrow depletion width. So what can happen is that these electrons can now simply, as we had discussed for tunnel diode, they can now simply tunnel through from here to here, right, from filled to the empty states, and thus current can start to flow, and a huge amount of current start to flow, because you can see there's significant amount of overlap. We have discussed this phenomena of overlap in the previous problem, right? And so current is, so now a current is starting to flow, huge amount of current in fact starts to flow, and thus this is again what we refer to as a breakdown. This is called a zener breakdown, based according to the person who discovered this phenomena. So but this is again in the reverse bias, you are seeing a huge amount of current flowing rather than the background of the leakage reverse saturation current that is flowing, right? And again this option is there that it needs p and high doping, because then only the depletion width will be small and your electron can tunnel through, right? So the third problem, the third part of this problem related to depletion capacitance. So this is what I am showing here. This is just a standard your forward bias. So actually let's call it reverse bias. So just okay. So this is the reverse bias that I am applying. Sorry, one second. So yeah, now it's a reverse bias. The positive terminal of the battery is connected to the N side. So this is the reverse polarity battery, and I've connected to this PN junction diode. So this is the capacitance that I've written. How I've written, you must be aware, capacitance is epsilon A over D. So there are these negative fixed charges and positive fixed charges in the depletion region on the both sides. Again, recall your depletion approximation, right? that there is no charges on the in the bulk regions, and only the charge is this abrupt transition between the depletion region and the bulk region. That's what we had discussed in the depletion approximation in the last session. So epsilon A over D, and I just normalize, if I normalize with respect to area, so what you get is epsilon over D, simply capacitance per unit area. The Cj is nothing, capacitance per unit area, so its unit will be farad per centimeter square. Okay, this is a dielectric constant. W is a depletion width, that is separating the two the fixed charge regions, and you just put the expression for W in this formula, and you'll get this expression. So as you can clearly see that the capacitance inversely depends on the applied reverse bias, which makes sense. If you increase the reverse bias, the depletion width will increase, and the depletion width increases, your capacitance inversely depends on the distance, so that should reduce, right? So that's what it's a square root of the dependence. So that's what we learn from here. So just to complete the problem, we know that so this is we had discussed so first we had discussed the avalanche breakdown, why it occurs, and it increases with increase in temperature. This is, by the way, also known as positive temperature coefficient. This was the correct option. We also know that zener breakdown needs high p and n doping, otherwise tunneling will not happen. The probability will be very low that the current flowing will not be high enough. Finally, we saw the depletion capacitance decreases when you increase the reverse bias, because as you can see, it inversely depends on the reverse bias, right? So if you increase the reverse bias, the depletion capacitance decreases. So these three options are the correct. And just to complete the whole picture, this is how a typical IV characteristics looks like. So this is called the knee voltage over here, and on the reverse side you have the reverse saturation current, and it breaks down. So this is, let's say, my V breakdown, and the zener diode breakdown is also there, but it usually happens at lower voltage. So this is, let's say, V zener. A good example of the application of a zener diode is as a voltage regulator. So this is usually, there are different versions available commercially which you can buy and use in your circuits. So zener diodes, for instance, they usually start from 2 or 3 volts or something. They can go up to as high as I think 40 or 50 volts, if I recall. So these are used as a voltage regulator. So this question can be asked, that like which of the following devices can be used as a voltage regulator. The options can be given as a MOSFET. We'll talk about MOSFET in the coming sessions. A zener diode, let's say an LED, and so on. So just, it's a good thing to remember that whatever is the application of a zener diode is. Okay, right. So the next question is that from among the 4 given materials, PN junction made of which of these materials will give the highest breakdown voltage? So these are the 4 materials that are given to us: gallium arsenide, gallium nitride, beta gallium oxide, also written as like this, and silicon carbide is these are all these 4 are semiconductors. So the question asks which of these will give the highest breakdown voltage. So when nothing is mentioned about the breakdown voltage, where here we are talking about the avalanche breakdown. Here we are primarily concerned about the avalanche breakdown. So if you recall, the mechanism of avalanche breakdown is that an electron comes, it knocks out so this is the lattice atom, it knocks out another electron, so there will be 2 electrons now, and this process continues, and more electrons will be produced, right? So essentially the primary thing among them is to knock out an atom of this lattice atom, knock out of an electron out of this lattice atom, right? So essentially what you're doing is you're generating a free electron. Alternatively, you can look at it this way. Sorry, just let me redraw this. Just look at it this way. This is our EC, this is our EV, and this is our EG. So this incoming electron must have sufficient energy to do this. It must create another electron it must take from EV to EC, right? So when will it be more difficult? It will be more difficult if EG is large, right? So if EG is large, kinetic energy of incoming electron must be higher, right? and higher means now that, please remember, the kinetic energy is half mv square, right? And this velocity v, if you recall, is v square equal to u square plus 2as, right? The acceleration term comes there, right? And then the acceleration terms, so what I mean is that v square equal to u square plus 2s. Let's ignore the u initial velocity, so it's 2as. And this acceleration, if you recall, comes from the force term, right? This force is the electric field that we are applying across, right? So this is, let's say, directly dependent on the force, and this force term is in turn dependent on your electric field E, right, which depends on the applied potential VR. Simple as that, right? So for higher band gaps you need higher kinetic energies, and thus you need higher accelerating potentials, right? In order to achieve that, you must apply higher reverse voltage, and thus V breakdown increases. It's very straightforward. If your Eg is large, the kinetic energy required is large, and in order to have a higher kinetic energy you need higher acceleration, which means you need higher reverse bias to be applied, which is the definition of the reverse breakdown voltage. So now, as I told, if you must remember uh, the the band gaps for them. So this is 1.4 ev, gallium nitride is 3.4 ev, beta gallium oxide is around somewhere around 4.8 to 5 ev, silicon carbide is 3.3 ev. So the highest band gap is for beta gallium oxide, and thus this will be our answer. This is the highest band gap, and thus it will have the highest breakdown voltage. This is essentially is also experimentally observed. Okay, so till this part we have talked a bit about the p-n junction in the reverse bias. Now when we go ahead, we will talk about I'll take up a problem on the application of the p-n junctions. So the next question, we have again, more than one statement may be correct, as I pointed out for the in the previous question. Be careful, try to attend these problems only when you are certain that you can get all the uh, options which are correct comfortably, because otherwise you'll be wasting your time, and when the probability is higher that you'll not get marks if you're not 100% sure. Okay, so for this problem we need to identify the correct statements. So the four statements have been given here. So we can so if you let's just have a quick look on them. So first option talks about led of the material silicon. Second option again led, but the gallium nitride, and we'll see what do we mean by operate, this term and these different regions. I'll come to that, but the first two problems concerned about the led. Third and fourth also talk about the led, and also another kind of device called the photodetector. So what I'll do is that I'll just uh, talk briefly about these devices, and just to be just for the sake of completion, if you refer to Professor Digvijay's video lectures, then you'll say that these devices come under something which are known as the which have been listed under applications of p-n junctions, right? So essentially there are three devices that are talked about are LEDs, light emitting diodes. It's a diode, light emitting diode. Second device is the, it's listed also in this problem, is the photo detector, and the third device that has been talked about is the solar cell. So of these, I believe you are very familiar with LEDs, and I suspect you must have some exposure to what a solar cell is, or at least its application. You must have seen the solar panels installed on, maybe on the rooftops of public places like metro stations, railway stations, and so on. Photodetector, another type of device. I'll talk a bit about this, but first let's talk about the devices called the light emitting diodes. Okay, so just let me, just for the sake of completion, I'll draw it here itself. So this is the IV characteristics of a p-n junction diode, the forward bias and the reverse bias. So I'm just not drawing the breakdown over here, but so this is the quadrant 1, as you are aware, quadrant 2, quadrant 3, and quadrant 4. So each of these the three devices that are listed here are operated in one of the quadrants. So this in the first quadrant you can see the voltage is positive as well as the current is positive. So I must define positive and negative. So this is PN junction diode, and let's say I'm applying some bias VA. So when VA is a positive entity, this means I'm operating in the first quadrant, and when the current is flowing in this direction, right, then also I mean I'm in the first quadrant. The third quadrant, for instance, this VA will be negative, which we are denoting with through VR for our discussion, and the current flows in the opposite direction, that is from N to P in the PN junction diode. In the fourth quadrant, what we see is that where solar cell is operated, so this is the solar cell quadrant, this is the photo detector, and this is the LED in the first quadrant. So photodetector is in quadrant 3, we'll talk about it, but LEDs are operated in quadrant 1, that is you apply a forward bias to the PN junction diode, which is what I have written over here, that when you bias the PN junction forward bias, so this is what you are seeing here. You can see this is not an equilibrium because this is the EFP, we have EFN here, and the rest EC and EV have been drawn. And what you are seeing is that if this is applying to the negative terminal of the battery, some electrons are coming, and then the electrons will drift across the depletion region. And you can also see that the barrier is very low over here because the VBI effective band bending is now VBI minus VA. So that's why you see this very reduced, more or less a flat region. So there's a large number of electrons will now drift across the depletion region and will recombine over here, which you are seeing over here. You must remember that when the electrons, for instance, travel on the P side, this is the P side, this is the N side. When they're traveling to the P side, there is an excess of holes in the quasi-neutral region, and the electrons will simply combine over here, right? And the concentration of electrons drops quite a bit gradually, exponentially rather, in the quasi-neutral region. We had discussed this in the last session. You can please refer to that or refer to Professor Digbijoy's lectures, right? So we see the recombination over here. What also can happen is that, right, is that they can recombine in this region. Okay, and this is one of the things that we try to do. Okay, now one thing is happening is that I've been talking about I've talked this term recombination a couple of times, right? So recombination is essentially, which is depicted over here, when electron falls from EC to EV, right? So when electron falls from EC to EV, this is usually referred to as a spontaneous emission. There are another class of devices called laser, right? So there's another class of device which works on stimulated emission. You must have heard about the lasers, like those for the people in presentations. They point out on the slides. They point with a pointer. That's a laser, right? And there are other powerful lasers which are used for many other applications. For LEDs, it's a spontaneous emission. This means nothing is driving it, so it's as if it's happening it on its own, which is true. So for instance, electron here will see a hole here, it will simply recombine, as simple as that, right? Now when it is recombining, so what is happening is that, what is the energy of this photon? H cut omega, or also the energy of the photon will be exactly equal to nu is the frequency of the photon which is being emitted. Or you can also, this formula by the way is, or has another form, like you can see Eg equal to hc upon lambda. C is the velocity of light, lambda is the wavelength, and if you just put in the numbers of the Planck's constant and Eg and the value c, so we arrive at an expression which I recommend you remember, that the wavelength in microns simply is 1.24 upon Eg in electron volts. So I reiterate, the wavelength in micrometers can be given as 1.24 over Eg. So because we remember the band gaps usually in terms of electron volts, for instance, gallium nitride has 3.4, gallium arsenide has 1.4, and so on. So you can simply put those numbers and you can get what is the wavelength of light that will be emitted by this material. Note, it's only depending, there are other factors also, but primarily it only depends on the wavelength, of the band gap of the material of which this LED is being made. Okay, so that's why you see only one term over here, eg, that's it, no doping, etc. These terms are not involved in that. Just try to remember this formula. This is very handy, comes in very handy, you can save a few minutes of your time. Oh, an important question, I just hinted at that. So in fact, when I was talking about this formula, I did not say silicon, or which is the most common semiconductor, or huge amount of semiconducting transistors and other devices are based on silicon, right? But light emitting diodes have a slight problem with that. So I'll try, we had talked about it, I think, in the second session or so, but I'll try to bring it up again so as to what I'm talking about over here. So let me first draw the band structure now. So if you recall the band structure, we are talking about E versus K, that is energy versus wave vector. K is 2 pi by lambda. So let me draw the conduction band first. So let's say this is the conduction band. Okay, and let me now draw the valence band. This is the valence band now, and let's say this gap, right, between the minimum of conduction band to the maximum of valence band is 1.4 eV. This means I'm drawing the material gallium arsenide over here. So this is how it's being drawn. And if just to reiterate, the curvature of this conduction band gives the effective mass of electrons. The curvature of the valence band will give effective mass of holes for the material gallium arsenide, and the band gap is defined as the point within the minima of conduction band to the maxima of valence band. This is what is known as a direct band gap semiconductor, which means the minima of conduction band perfectly aligns with the minima of valence band. You can see it's not shifted, and you'll be able to appreciate it more. So let me just say these are what is known as, excuse me, this is what is known as direct band gap semiconducting materials. Now let me draw what is the example of an indirect band gap material. So again, I'll draw the E versus K, and this is for indirect. In the blue, I have the indirect band gap materials. A good example, let's draw for silicon. So again, let's draw the conduction band first. So this is the conduction band, this is the minimum of conduction band, and let's draw the valence band now. So let me draw the valence band for silicon. So this is the valence band. Sorry, it's a mistake. Since silicon is an indirect band gap indirect band gap material, so what happens is that there the minima of conduction band does not align with maxima of valence band. You can see that. So this is some at k prime, let's say, and this is at k equal to 0. So the minima of conduction band lies at k equal to 0. The maximum valence band lies at some k equal to k prime. This is not, the wave vector is different. Hence this is an indirect band gap, and this again, by definition, this is the band gap, and this will be 1.1 eV. So the band gap, the definition of the band gap remains the same, minima of conduction band to the maxima of valence band. In the y-axis, that is, because remember, energy is on the y-axis. So you can see that now, if an electron, let's say an electron is residing at this minimum of the conduction band, over here, and it has to come to valence band. So what did it do? It will simply emit a photon of 1.4 eV and just come over here, right? So what we have is, for direct band gap materials, so what we have is an electron photon interaction. For direct band gap materials. What is the case with indirect ones? For indirect materials, for indirect band gap materials, let's try to do the same analysis, right? What will happen? So again, if an electron is here and we have to bring it here, let's say, what it will do, it has to lose first of all 1.1 ev. So first of all, it's an electron that is being, that is the material in question, and again we need a photon, right? Because we need to emit this 1.1 ev of a photon, that is the energy drop. Also we need to traverse this distance, this k, this sorry, k prime minus 0, which is nothing but a phonon, because this momentum, this change in momentum must be supplied by something. Photon does not have any momentum, it does not have any momentum. So for an indirect band gap material, the emission of a photon, uh, the recombination, rather the process of recombination, must involve an electron photon phonon interaction. For an indirect materials like silicon, another example for an indirect band gap material is germanium, right? So for these kind of materials, it is what is referred to as a three particle interaction. The probability of this, first of all, this process is inefficient, and the probability is also very less. So even if you make a led of silicon, right, the recombinations that are happening, the percentage of recombinations that is happening, this will revisit this in a bit more detail in the further sessions. But just to reiterate that it's highly inefficient process, being a three particle interaction. On the other hand, for direct band gap materials like we have as a gallium arsenide or gallium nitride, this is efficient process. Okay, so this is just a snapshot of what is a light emitting diode is, how does it function, and what is the role of a material in this case. So what band gap can you choose, or what is the nature of the band gap, it should be direct or indirect. So we test up upon them, and now we can at least answer the first and second option for this. So led made of silicon can operate in infrared region very efficiently. The problem is very efficiently, no, it cannot, because silicon is an indirect band gap material. But let's just still try to find out what kind of photon will be emitted. So as I pointed, the lambda will be 1.24 upon Eg of silicon, right? If I interested lambda of silicon, so 1.24 upon 1.1 ev, if you try to solve it, it will be around 1.1 microns. Please remember the units here are micron. So 1.1 micron. So this so if you recall, your visible wavelength is 400 nanometers to 700 nanometers, right? So visible is 400 nanometers, that is zero point 0.4 microns to 0.7 microns. So this is higher than 0.7. So we are in infrared region. So that part is correct, that it is the photon will be emitted in the infrared region, but that will be inefficient. So this part is wrong. So option A overall is wrong. Let's try for gallium nitride. So photon emitted for a gallium nitride based LED will be 1.24 over Eg of gallium nitride. So gallium nitride has a band gap of 3.4 eV. So if I try to calculate it, you'll get it 0.365 microns. Again, visible is 0.4 to 0.7. So 0.4 corresponds to violet. So this wavelength is below that. So that means we are in ultraviolet region. So this is correct. And this can be efficient because remember, gallium nitride is a direct band gap material. So this option is correct. And I've already pointed this out, that among the various devices which are based on PN junctions, so LED is operated in the first quadrant, that is you apply a forward bias to the LED and you have recombination and so on and so forth, you get a photon out of it. Photo detector we have seen is operated in the third quadrant, right? So this option was incorrect, this is part is also incorrect, this is correct, and this is also correct, right? So option this third option is correct. So 2 and 3 are the correct options. But let's just not pause here, and let me just give again a brief introduction as to what a photodetector is. So as the name suggests, a photodetector, you are detecting a photon, right? So that is of particular importance in some applications. A good example is, for instance, an IR imaging, infrared imaging. Right. For instance, when the COVID was at its peak, and the and the respective state governments and the new union governments relaxed the measures and the people started to travel, you would have noted that there was a camera or a person sitting behind, noting down the temperatures by scanning your forehead or something. That was true at bus stations, metro stations, railway stations, and so on, and airports. Right. So they use something called the infrared imaging, right, using that thermal camera. And this is also beneficial in wildlife research, so where they need to trap, for instance, movement of animals which usually come out at night when the temperatures are lower. It's much cooler. So there it's very efficient. There it's this application is there of IR imaging. And there are other applications also. You want to detect, for instance, the cosmic rays from the outer, from the outside the earth, the waves that are coming, right? What is their composition, what is the wavelength, and so on. So in that again, this is different materials are used, yes, but at least, for instance, we saw the ultraviolet, you can use the gallium nitride, for instance, right? So such applications are there where photo detectors are used. Okay. So how are they used? So let me just talk about that. So first, let me first draw the IV characteristic of a typical PN junction. So IV, okay, and this is your the reverse side behavior. Okay. So what in the photo detector community, what they refer to as is the, so this is the, what is the dark current. Let me just a second. So this current is referred to as dark current, means no photon is being shined. So this is your, again, simple PN junction. You are applying, this is, as I told, this is primarily operated in a reverse bias. So you are applying a VR over here, and you are shining light. When you're shining light, we'll see what happens. So very small amount of current will be flowing. So in order to just illustrate my point even further, so what I'll do, I'll just assume that we are operating in the regime where the device is not breaking down. It's happening at somewhere over here, but I'm not interested in that. I'm just operating, we are operating in the safe regime. VR is not high enough. Okay, so now let's shine some light on it of a particular wavelength, let's say. Okay, so what's going to happen when the light is shining? So there's a depletion region over here. So what will happen when light is shine, electron holes pair will be created, as simple as that, in the depletion region. And there's a strong electric field which exists, because remember, we are in the reverse bias, so electrons and holes will be swept away. So what's going to happen, the large number of electron hole pairs will be generated, and what you are going to get is something, the current will increase. So let me show the increased current by something like this. So again, I'm operating in a regime which we are safe, we are not breaking down the device yet. So it will look something like this, right? And let's just say, so I'm shining some light of a given frequency, and let's say the intensity is, let's say, low intensity. Note, intensity is different from frequency in the sense that frequency denotes the energy of one particular photon. Intensity determines that how many photons are you bombarding on this device per unit area. Okay, it will a specific area. So let's say you are bombarding 10 to the power 6 photons per centimeter square, let's say. Okay, now what I'll do, I'll increase the intensity. Let's say now I increase the intensity 10 to the power 8. What's going to happen, now I'm bombarding more photons. So what's going to happen, more number of electron hole pairs will be generated, and if VR remains the same, then what you will see, the current will increase. So let me call this, the blue curve, as the high intensity curve. Okay, let me just extend this line, right? So what you can see, why it, now you will be able to appreciate why it's operating in the third quadrant. In the first quadrant, because there'll be combination of two components over here, right? First is due to electron hole pairs, and due to the typical or drift diffusion, whatever the standard working of a p-n junction diode in the forward bias. So it's two effects are being compounded here. In the third quadrant, only the current depends only on the intensity and nothing else, right? So thus you can detect if the current is this much, the intensity of the photon should be this much, so on and so forth. The frequency again is the frequency should be such that you are able to generate electron hole pair. What I mean is that if this is EC, this is EV, so this is the EG, so H nu should be greater than equal to EG, then only you will be able to generate the electron hole pair. So that is again of importance. But let's assume that we have chosen such a material of a given application, right? That for we want to detect some let's say ultraviolet radiation, so we'll choose such a material, we'll fabricate this, and if we increase the intensity of the incoming light, you can see an increasing intensity in the current, and that's why it's a detector. The higher the intensity, the higher the current, and you can say, oh, these many amount of photons are bombarding our device. Okay, so this is a very interesting application. A lot of research happens in this field rather. Okay, so that is all. So now I'll stop here because of the p-n junction part is over. Now we'll see a different now two terminal device for our next discussion. In order to understand the Schottky contacts, which is the next uh, device that we are going to study, the Schottky diode, which has Schottky contacts, there are a few terms which appear over and over again. So I'm just using the next couple of questions. I'm just trying to establish those concepts or those entities. So first we have this term appearing called the work function. You may have heard about it in some other context, but I'm going to restrict myself to the semiconductor physics world as to what the work function means in this regime. Okay, so there are different options given, but just to illustrate different points, that is how to identify that. So what a work function is defined as, so in this case what you see on your screens on the right is a metal. So as you can see, there is a first of all there is a vacuum level that we have defined, that is the electron is free at this level. Okay, does not feel the it's an arbitrary level you can define, but essentially it's that the electron is free. After, if you recall, in the very first session we had talked about a free electron, right? And in this, we are taking a case of a metal, so you can see the Fermi level is defined, noted by this dotted line, and the metal is filled up to that Fermi level, and the difference, energy difference between the vacuum level and the Fermi level is defined as the work function, which is given by this function phi. So phi is the work function, which the units of this is expressed in terms of volts. Alternately, you can see sometimes in terms of electron volts when you're talking in terms of energy. So that's why here is referred in terms of volt. And so it's, again, to reiterate, the difference between the vacuum level and the Fermi level for any material. I have given the case of a metal here, but we'll evolve this concept and extend it to different materials, even semiconductors. So between vacuum level and the Fermi level, so we have energy required to move an electron from EF to the vacuum level. So this will be a correct option. Okay, now second concept which I want to introduce for this session is the electron affinity. Again, you may have heard this term, especially in the context of high school chemistry, but I'll redefine it for the semiconductor physics world. Okay, so first let's just identify the material in which we are talking about. So as usual, I have drawn this vacuum level, and just concentrate on the right side, forget about these chi or phi's. Let's just look at this material what we are talking about here. So you see an EC and an EV, right? And there is a band gap, so clearly this is a semiconductor we are talking about. And we have also drawn the EI, the intrinsic band gap, which lies at the midpoint of EC and EV, right? And there is ef is the Fermi level for this material. One thing you can clearly notice is ef is closer to ec, right? First of all, ec and ef, there is a band gap, so this means this material is a semiconductor. Secondly, since ef is closer to ec, this we have seen for extrinsic semiconductor, since ef is not at ei, so this is an extrinsic semiconductor, first of all. Second of all, is it n type or p type? Since ef is closer to ec, right, we can say that this is an n type semiconductor. All right. Now, as we had defined the, if you recall, the the work function. So work function is between the vacuum level and the Fermi level. So again, you see this symbol phi s. So this is our work function. Work function, if you recall, is the energy required to move an electron from Fermi level to the vacuum level. So between E0 and EF is your phi s. Mathematically, it can also be written as E0 minus EF equal to E phi s. What is electron affinity? So electron affinity, again, mathematically I can write is E0 minus EC equal to E chi. So this is the EC level, this is the E0 level, and this is the electron affinity. So these are the two terms that will especially for the next few slides, for the remainder of this class, I'll just reiterating these concepts. Okay, so now let's build up on this and form what is called, till now we have seen a junction. In a PN junction we had one side P and the other side N, right? Now we are going to see a different kind of junction called a metal semiconductor junction. Now a question that might rise, if you recall, that we had always biased um, the PN junction diode, right? But we are, what PN junction semiconductor material, for instance, P side, let's consider only the P side, it's a semiconductor material and it's connected to a battery using, let's say, a wire. So how does a wire make a connection with semiconductor material? It's essentially a metal semiconductor junction. And then we had the PN junction, semiconductor junction, and again on the N side was connected to a battery using a wire, right? So again that was a metal semiconductor junction. Okay, so essentially what I'm going to do is we have metal on one side, and in this case I'm taking an n-type semiconductor, which you can see that EF is closer to EC. We have already talked about this. So this is a metal semiconductor junction I'm talking about. Okay, and it's just that in this case you can see that phi m is greater than phi s. Again, they have not yet made contact, but this is the case. In this slide what I'm talking about is phi m greater than phi s. This distinction is important. We'll see in a minute why is it important. So now let's make contact. So what's going to happen, there are different ways of expressing that. The way I'm going to say is that since EF is your, let's say, your, with the probability of finding an electron is half, and you can clearly say when these two materials are made in contact of each other, right? So what's going to happen, the Fermi level has to be horizontal. We'll assume first of all we're not applying any bias, just like we did PN junction case, we just let it be at the equilibrium. So it's going to happen, you can see some electrons are going to flow from the N semiconductor to the metal side, right? So how will the electrons come from? Obviously this is N type doped material. We have donors and we'll assume 100% ionization again. So the electrons from the N semiconductor will now the mobile electrons, that is, will now go towards the metal side, and they'll just dissolve in this the huge sea of electrons that we have on the metal side. But will the electrons leave behind? They'll naturally leave behind a positive charge donors. It's very similar to what was happening in the concentration gradient when we had PN junction, right? The electrons from the N side were traveling to the P side, they recombined, they form the depletion region. So again, the depletion approximation that we saw there, that the electrons have traveled from this region and they leave behind positively charged donors. So this assumption is again valid over here. We are borrowing the same depletion approximation. On the right, on the extreme right, what you can see is that the behavior still retains it's pure n-type characteristic, the bulk characteristics, right? So this is just like the bulk, just like we had the quasi-neutral region in the p-n junction. A very similar principle we are using here, right? And now you can see that ef is aligned on the both sides. Again, you can see that we are not applying it any bias here. So again, as just to reiterate, this is again the case for phi m greater than phi s. But you see here, you can see a barrier that is forming, right? So when I try to bias it, let's say now I apply a positive, you again see the first of all the built-in potential. Now you can apply a forward and reverse bias, and accordingly the band bending will be changing. So when you apply a forward bias, that is you connect the metal to the p side and the semi n-type semi to the n side, what you're going to have is this band bending will reduce, so it will be vbi minus va, let's say. If you apply a reverse bias, for instance, this band bending will be more severe. So the band bending will be VBI plus VR. It's very similar to what we had seen in case of PN junction. So I just draw a simplistic picture at equilibrium. The rest of the changes that happen when we applied a forward bias and a reverse bias, those principles of the band bending will still be applicable for a metal semiconductor junction as well. Now, I told you we had been talking about phi m greater than phi s. So this, in both the cases that you see on your screens, are phi m greater than phi s, right? And you can see a barrier that is there. You know, this is like a wall. So electrons will have to now. So the electrons which are here, let's say, if they have to travel to the other side, they have to cross this barrier, right? And vice versa. If the electrons, let's say, if they've crossed from here to here, let's say we are applying a forward bias, that is metal to the p side, so there'll be holes which have to traverse, or let's say the opposite side, the electrons have to travel from this side to this side. There's still an energy barrier that it has to face. This barrier is also known as the Schottky barrier, essentially. Okay, so now I'll take another case, and I'll take in the case of, let's say, phi m, which is now less than phi s. So essentially this is just a before contact, right? So what's going to happen, this picture will remain the same as it is. I mean, this is just before the contact. After contact, how will it be? So again, let me draw first of all the junction, right? So this will be the ef, the metal side, right? And what you will see is that since phi m is greater than phi s, so the electrons will have to travel from the metal to the inside, right? So what we see, what we observe is a junction forming something like this. ef will be still be the horizontal, because again I'm not applying any bias, and this will be ec, right? And below there somewhere will be your ev. Okay, now what you can see that in this region, just in the notch, this is in this region, this is the electrons which are here, the electronic states which are below ef. So there is a very high probability of occupation, and thus the concentration of electrons, right, is very high in this over here. So there is a huge amount of electrons that reside in this well, so to speak. Okay, in this, because why it's happening, because first of all phi m is less than phi s. So when you make contact between these two, so the electronic energy is higher on the metal side, they'll naturally go to the end of semiconductor. So this is E naught, by the way, the vacuum energy level. And so what's going to happen is that you will form this kind of a system. Now this, as I told, this is phi m less than phi s, and this is the analysis for phi m greater than phi s. So these are two different nature of contacts. Again, I'm just drawing for metal and n. Similar exercise you can do for metal and p. Again, based on the relative work functions of the metal semiconductor side, you can form two different flavors of contact. So this flavor in the blue is called non-rectifying contact. In the red, which we had discussed earlier, this one is the rectifying contact. Rectifying contact's behavior is very similar to that of a p-n junction, something like this, IV characteristics. On the other hand, for a non-rectifying contact, what you can see is that when you apply a bias, right? So it's going to happen, this will shift. Yeah, naturally this will shift a bit up or down, but still the concentration of electrons will be huge. What it means is that even if applying a forward or reverse bias, there the huge amount of electrons always available. It's behaving like a metal. So metal, as you change the potential, these electrons are free to move here and there. So that's why you can see, you can get a large amount of current in both the directions, forward as well as reverse bias. Same goes here. There's a huge amount of electrons in this well that are available. So what's going to happen is that it's going to behave like an ohmic contact, something like this, a straight line, I versus V. So this is non-rectifying. So as I told you, in a PN junction diode, right? So let me complete the analysis. I'll use the purple color. So when we had this PN junction diode, and let's say when I was biasing it, forward bias, how is this wire connected to the P side, right? I want this to be not at this type of a junction where it can present a barrier. I want it to be as smooth, as ohmic as possible, so that it can facilitate without acting on its own, without acting its own peculiarities. It should allow the flow of electrons and holes either way. So these contacts that you see on these sides, this and this, these are made non-rectifying or ohmic in nature. And how do we do that? We do it in such a fashion. We choose such a material because see, phi s is fixed. Let's say if it's silicon, so phi s is fixed. But you can choose a metal. There are different metals that are available: titanium, aluminum, nickel, tungsten, so on. Right? You can choose these materials as that phi m is such that it will be less than phi s, and we make a non-rectifying contact on this, where p-n junctions are to be connected to the battery. Right? Otherwise, if you want to make a Schottky contact, we'll see the advantage of Schottky contact in a while as compared to p-n junction. But if you want to make a rectifying contact, that is, it conducts only on the one side and not on the other. Remember, we had started p-n junction comparing to an ideal switch, right? So this is something like that. So rectifying is that it will allow the flow of current only in one direction. We are neglecting the breakdown voltage for now. So this is the rectifying and this is the non-rectifying. Please keep this analysis in mind. Okay, right. So now let's put our that understanding which we had, like depending on the two flavors of the contacts. So now it says a Schottky diode has two contacts. So let's just make the Schottky diode. By make I mean let's draw a schematic of the Schottky diode. So on one side we have metal, and on other, let's say I have n-type semiconductor, and these are the two on the left and right which I have highlighted. And these, from here it will be connected, it may be connected to a battery for forward or reverse bias. For let's for now, let's say it's not connected, so this must be at equilibrium, right? As I told in the previous analysis, so first I'll assume that the metal semiconductor junction here, right, this will be a Schottky junction, Schottky contact. Okay, I'm assuming this to be a Schottky contact, and this is a metal wire, let's assume. So metal contact will be ohmic. Okay, and this one, as I told, I want the analysis of the region in which I'm going to highlight in purple. So I want the analysis of this region, right? What I don't want is all these outer things to play a role. So hence I should make all the other contacts to be like conducting in both the direction. They should have minimal role. They should not act any resistance or any external thing. Essentially, we call them parasitics. So there are, apart from parasitic, there are other considerations, but I don't want them playing a role. So what I want is that I also make this contact an ohmic contact. Okay, so if you look at this whole device, right, so here it's a metal contact. Again, this wire I'm assuming to be metallic. So we have an ohmic contact on this side, and I want to analyze the Schottky diode. So the Schottky barrier or the junction that I'm forming, I will form it as a rectifying one if I want, that is. right? Otherwise this will completely, if I don't make this rectifying one, then this will be metallic, so it essentially I made a resistor if I also make this rectifying. So I want to analyze this, and I'm assuming this is a rectifying contact that I'm making. On all the other contacts, especially when it's connected to the battery, I need to make them ohmic. So in this case, this is fine, this is understandable. You have, let's say, fused the two metals, soldering or whatever. Here, how do you do it? From metal and so this is semiconductor and this is metal, this wire is metallic. We make a Schottky contact which is non-rectifying. We have already talked about it's a non-rectifying. So let's say this is metal MW. Okay, so we have seen that this, and for rectifying I'll make phi m less than phi s. Please remember, phi's are the work functions, so phi m is greater than phi s will make a rectifying contact. And for this metallic and for this connection with wire, I'll need to make it non-rectifying or ohmic in nature. So what we see is that in this Schottky diode, one of the connections is Schottky in nature, the typical Schottky that we encounter, while the other terminal is ohmic. So this is a Schottky diode. Okay, so we see one contact is Schottky and the other is ohmic. So as I was illustrating in the previous slide, and when we make an NPN junction, right? So let me sorry, PN junction diode. So this was the P side, this was the N side. So what kind of contacts are we making here on the left and right? Again, the region of interest for me is, again, which I will highlight in purple, is this. This is my region of interest. So all the other parameters, I don't want them playing much role. Okay, so what I'll do is I'll try to make these contacts ohmic. But ohmic, as we understand, is kind of a metallic in nature. So how do we connect this metallic wire, this wire on the both sides with the semiconductor? We have to make a metal semiconductor junction, and we'll make it non-rectifying. Non-rectifying, both of them. So how do we do it in practice? So it's really straightforward. You know the semiconducting material, you know phi s, right? And you choose as metal such that phi m is less than phi s. So you choose such a metal to make the non-rectifying contacts. That's how we do it in practice. Yeah, so this was the yeah, so this is what I mean. I just illustrated that. Now how is the carrier transport happening in this case? So just on the top you have to just make it more similar, so on the top you have a P plus N junction diode. Why I'm doing this is so that it closely mimics, at least in concentration wise, you can see that it's a P plus junction. So first of all, it's not an equilibrium. You can see the EFP, which is this dotted line, is not EFN. So this means we are not in equilibrium. And also it's in forward bias because you see a large concentration of electrons that is residing on the conduction band on the N side. All right, so we do that, and we have seen that that it's actually the electrons are injected on the N side when it's forward bias, p-n junction, injected on the N side, and then finally they for the as there is a depletion region, so they drift across the depletion region, and as soon as it is the P side, they recombine in the in the bulk or the quasi-neutral region of the P side. But there is very minimal diffusion that happens across the depletion region. It's primarily the drift of the mobile carriers. Please remember that. So that's why I say the J and diffusion is negligible in case of a p-n junction diode, or for that matter P plus N junction diode. In case of a Schottky contact, a rectifying Schottky contact, what happens is that the dominant mechanism that is there is thermionic emission. So what we have is that we have electrons. Let's say, again, you can see the Fermi level is not constant because this is the Fermi level of the metal, this one. The Fermi level here is slightly higher. Okay, so what's going to happen, that the electrons, if they can cross this barrier, they can reach over here and thus contribute to the circuit will be complete, and a current can be flowing. right? So the emission over this barrier, the Schottky barrier that we talk about, is the thermionic in nature. It comes from thermal plus ionic. This means it depends on temperature. How it depends on temperature? It just so happens that the nature of the expression is very similar to what we had obtained in case of a PN junction diode. So J is again your current density. So J is your I over A, current over area. So amps per centimeter square will be the units. And GST is the again the reverse saturation current is similar, as I said, the form is very similar to what we have on the PN junction diode, and that's why I told you that it allows the current to flow on the forward side and blocks on the reverse side, which is the nature of a rectifying contact, very similar to a PN junction. So, but the one thing that is different is the reverse saturation current that you see, current density in this case that you see. Its form is slightly different. So there's a t square component here also, and this is again similar to, if you recall, minus Eg over 2 kt. So that form is a bit similar, and this phi b is your Schottky barrier that I have been talking about, right? So in some aspects it's different, right? I'll talk a bit more on a bit differences a minute later, right? But let's just complete the analysis on the mechanism that is dominant in the case of a of the operation of a Schottky diode, right? So we need to find the mechanism of current transport when a Schottky diode is forward biased. So as I've talked about, that it's not drift and diffusion, which is which in fact it is the diffusion of the, sorry, yeah, diffusion of the majority carriers, then drift across the depletion region, and then the recom and then the diffusion on the other side, which is in the case of a PN, right? This is the PN junction. Tunneling we saw that was happening, if you recall, in your what's called the tunnel diode that we had seen, right? What we see here in case of a Schottky junction is the thermionic emission of the majority carrier. So you see, if you recall, the electrons are there being collected on the over here, and they cross this thermal barrier, they cross this, sorry, energy barrier over here by the virtue of thermionic emission. I should add one more point, is that can I do it here? Okay, let me try to do it here itself. So let's say this is at present at equilibrium. So this is your EF, EC. I'm going to stick to the your uh, metal and n-type semiconductor with phi m greater than phi s. So this is now at equilibrium, you don't see, but now let's dope it very high. So if you recall, what you dope semiconducting material very high, the depletion region shrank, right? I just need you to recall the expressions for the depletion widths and so on, right? So there the depletion region shrank. So what's going to happen is that it may so happen, in fact we do observe it, when you dope it very high. So what's going to happen is that this region, which I'm drawing in blue, becomes, sorry, try it again. When we dope it very high on the inside, so what happens is that it becomes something like this. So this becomes the new EC for high doping. And now what you can clearly observe is that the depletion width has reduced, and if it reduces to a few nanometers or so, you can also have tunneling. So in that case, tunneling current also contributes in addition to the thermionic current, just like we saw a similar thing happening for the tunnel diode. Remember, when the current increased, and then we had negative resistance portion, and the current increased further when the drift of the carriers took over. So such a thing can happen here also. But otherwise, if nothing is mentioned, we'll assume moderate doping. And in the forward bias condition, a Schottky diode will have the current transport mechanism is thermionic emission of the majority carriers. right? So finally, as I was telling, in the comparison to a p-n junction diode, right? So this is the thing that we have here. Sorry. So what we have here is that, so we need to analyze in terms of two parameters. So first is the transient response, and the second term is the reverse saturation current. So reverse saturation current is simple to see, because that depends on the material parameters to a great extent, and doping also, rather. But if we assume the doping to be the same as compare in a p plus n junction diode versus, let's say, metal n diode, metal n semiconductor diode. So what we see is that, due to the terms that are involved, the reverse saturation current is high for a Schottky diode. The Richards constant that is there in the expression for reverse saturation current for your what I'm saying, reverse saturation current for a Schottky diode. That term, it's a t square dependence, and the other term in the exponent. All these contribute that the reverse saturation current is high for Schottky. Okay, so in fact, this is not true. This is not true. It is high for Schottky. The other thing we need to compare is a slower transient time. Okay, so this I need to um, illustrate a bit. So what I'm talking about here. So let's say you are operating in some forward bias. Okay, and then you switch it to the reverse bias, and then after a certain point of time, again you switch it to the forward bias. And so you are doing such kind of let's say you have such an application, right? So this is the V applied, and this is time, let's say, and again you are doing this exercise on a PN diode as well as on a Schottky diode. So what actually happens is that, so in the forward bias, what we can see is that usually the barriers are such that so this is your I versus V. We are talking only in the forward bias. So this is your typical, let's say, PN, right? However, this dotted line will be for Schottky. This is for a Schottky barrier diode. So they have a much lower knee voltages, so to speak. Okay, and what I was alluding here is that, when you apply the same voltages, and let's say when you are switching, so what happens is that, when in the reverse bias, so in the reverse bias, if you recall, in the PN junction, in the forward bias, when you apply so there will be the electrons will be drifting from this side to this side, and holes will be drifting from this side to this side. And let's say, as all of a sudden you put it to the negative bias, all of a sudden, here it was fine, but all of a sudden you put in negative bias, this will take some time to clear out this charge. Remember, this is the depletion region. In the reverse bias, no charge should be sitting here, right? So it takes much more time, right, to clear out these charges in case of a PN junction. So essentially, think of it this way: the currents are higher for any given voltage, for any given forward bias. Current will be higher for a Schottky barrier diode, right? You can see, let's take this voltage. So this will be your PN junction, and Schottky diode will be much higher, the current there. So current, it will take much lesser time to clear out these charges, correct? And that's what we have here. In case of a Schottky barrier diode, the transient time, the transients are much faster, right? So this is what we mean. Schottky barrier diode has a faster transient response as compared to a p-n junction diode. It's just that the current values are higher, and they can flush out any remnants which are there, especially when you're switching from forward to reverse. So they can flush out all these charges, and depletion cannot have any mobile charge carriers. Please remember that in the forward bias. In the reverse, in the forward bias, there will be a drifting of electrons and holes, but when you switch in the reverse bias, it cannot be there. Okay, and secondly, when you switch again from forward reverse to forward, it takes much less time because the currents are higher, so that again the electrons can come quickly rather in this region. So these are the key differences between a Schottky and a Schottky diode and a PN diode. Okay. We're running out of time, so let's just quickly look at the some formula which are frequently used for a short problems related to Schottky junctions. This is just the before and after diagrams that I have seen already in the previous slide. So this barrier that we see over here is simply the metal work function, which is the phi m. If you recall, phi m was between the work function of the metal, that is between the vacuum level and the Fermi level, minus the electron affinity. So this is the phi b naught that I'm talking about. On the other hand, VBI, the built-in potential, that is the band bending that you see over here, is simply phi b naught minus phi n, which is pretty evident from this. VBI plus phi n, because Fermi level has to be horizontal when there's no bias is applied. The depletion width is simply what you see. If you don't recall this formula, just remember the p-n junction from the previous session. This was the expression that we had used. Here we only have doping on one side, so we drop 1 over Na term, and you get 2 epsilon I. Q is replaced by E, the electronic charge, VBI over ND. So these are the three expressions that we typically use for solving some numericals. And let's quickly get into the first one. So we have a Schottky contact between the metal tungsten and the n-type doped silicon. The doping is given at 300 Kelvin, so we'll assume complete ionization. The electron affinity, work functions, etc. given. And this is the diagram, and we are required to find the built-in potential. So built-in potential is simply the barrier, that is minus this phi, and that is the EC minus EF. But we don't know the barrier, so we can get the barrier by phi m minus x. The metal work function is 4.55 minus, sorry, not x, chi is given to be electron affinity is 4.01, so that will be 0.54 volts. You put this value here, 0.54. How do you get phi n? So phi n is nothing but EC minus EF. So but if you recall that this expression, the carrier concentration one, so exp EC minus EF, sorry, there's a negative sign here over KT, it's actually EF minus EC. N is nothing but the electron concentration, which is equal to doping. So you put 10 to the 18, and C is 2.8 10 to the 19 exponent of EF minus EC over KT. You get this, from this you can get EC minus EF, right? This will be KT over Q times ln 28, right? You get this, so this is going to be around, if I get this is coming out to be around approximately 0.9 volts, sorry, 0.09 volts. You put this value here, you should get 0.45 volts. So we have this option. The built-in potential here is 0.45 volts. Again, what is the height of the barrier will depend on the metal that you're using. So using tungsten, which has this much per function. If you choose a different material, your barrier will change, and similarly your built-in potential depends on barrier as well as the doping level. So you change the doping levels, your built-in potential will also change. So the second problem to that is that we need to require the maximum electric field intensity. So again, the electric field intensity, this is again borrowed very similar to what we had seen in the p-n junction diodes. So what we have here is just the W will be equal to Xn, because there's no XP. The depletion is only on the N side, right? So what we do is that we put all these, so we need to find just the magnitude of it, right? So this I can say will be Q and D over epsilon, and this 2 epsilon VBI over Q and D, right? So it will be 2Q and D VBI over there will be an epsilon, 2Q and D VBI over epsilon. So you just you just plug in the numbers, and I believe what the answer is 3.8 into 10 to the power 5 volts per centimeter, which is this option. All right. So that's it for today. I'll see you again in the next session. Thank you.